Okay, so we're going to get started. This is part of the day that we're going to do something a little bit different, a little interactive and dynamic. So I do want to first off by thanking Cadence for hosting the event today, and Jan and Dennis and Stan for all their hard work. We're looking forward to a dynamic interactive session here. So we're not going to do sort of a traditional presentation. However, we're going to, as you can probably tell by a lot of the stuff getting set up here, we're going to break into some groups and have some good dialogue and discussion, and we're going to hack a problem for the EDA and IP. So that's a big picture of me, although. But I'm Karen McCabe. I'm with the IEEE, where I work in their standards division. Been there for close to 25 years, working with our technical communities, which includes our standards developing areas, as well as working cross-functionally with the organization, and more recently getting involved in some technology policy aspects of the intersection of where technology hits policy and what that means. But the good part of what I really enjoy doing is working with groups like this and having these types of interactive sessions. We like to call them the unconference type of events, so we can get the community to really start talking to each other and to produce some good outcomes about the future of an industry, as well as how to solve some problems in a collective, dynamic way. So figure it's like real-time crowdsourcing, right? So last year at the EDA Symposium, we held a similar session, but that one was focused on more of a visioning exercise. We were looking at the EDA industry from where would it be, and if you opened up the newspaper 20 years from now, or maybe it's not a newspaper because 20 years from now we don't have newspapers, but you're a news vehicle, and what the EDA industry might look at that way, knowing that it's been explosive, it's been dynamic, great things are happening, and trying to vision out and tell the story of, well, why did that happen? And what were the driving factors and potentially the challenges that might have come out of that. So there, as I mentioned, we were looking at 20 years out, EDA industry is exploding, it's wonderful, everything's great. What were the drivers, but also what might have been some of the challenges associated with that. So this is sort of an asset of what we produced. We did a lot of whiteboarding last year as well, and we have a better version here that you can see. But basically, we were looking at the various drivers ranging from globalization to technology to what might be going on in the various industries of healthcare and cloud computing and genetics, you name it, and how EDA is being used in those different types of industries and whatnot, based on looking at this. Well, these are the drivers. These are the potential outcomes of what we're looking at maybe 10, 15, 20 years from now when it comes to the EDA industry. And then, of course, noting, well, to get from point A to point B or point A to point Z, what would those challenges be? So we captured that. Today's effort is to kind of take the work that we've done last year and expand upon it. So before we get started, how many people were at last year's EDA Symposium? Okay, remember kind of doing this, all coming back to you?
I don't remember this part.
Dennis doesn't remember this part. Okay. So today, as I mentioned, we're going to build upon the work that we did last year. And don't worry, if you weren't there or you don't remember, it's okay. But basically, what we're looking to do with the EDA Symposium is to build really good content to address the EDA's challenges and how it could grow as a community and as an industry. And no better folks to work on that than the people who are right in the middle of working in this industry. So we're calling it a growth hacking for EDA and IP event today. We took some liberties with the term of growth hacking. It was initially coined, if you will, back in 2010 by Sean Ellis, really about a growth hacker as a person whose true North Star is really on looking on growth and how to realize growth in various technology industries. As you can see here, also it's about a mindset. It's using a combination of data, creativity, and curiosity. And it's really also Wikipedia's formal definition, and I know some people may have challenges with Wikipedia, whether that's formal or not, or official, I should say. But it's really viewed as a marketing technique developed by technology startups. So we, at the Standards Association, working in partnership with our EDA meeting planners, we took a little liberty here in kind of redefining it because we like the term growth hacking. And we do feel that it goes much beyond just a marketing technique. So as you can see, we're calling it growth hacking is a technique developed by the technology industry which applies creativity, collaboration, analytical thinking, and data to open markets, gain exposure, develop and sell products with global benefits. So we're using the concept of growth hacking to hack the problem of what are the challenges regarding growth in the EDA industry and how we can reach and realize that growth and overcome those problems. So initially, we were going to have 3 breakout sessions, but we are going to change that to 2. So as you can see, the room is set up, and it's a little bit of a challenge, but we will work through it. That we'll have 2 groups, one over here and one over there where the easels are. We have some tools, if you will, creative tools. We are capturing this through also a graphic capture of our discussions and events that will create a nice artifact after the event, and that will display it during the reception post this, but also we can do things moving forward with the EDA Symposium and how we can leverage the work that comes out of today through the year and for next year's event as well. So there'll be 2 breakout sessions, one on EDA and one on EDA and IP and sort of that interaction between those 2. So sort of we'll do Dennis will take on EDA and IP. You're going to be here, since you're sitting here. And Yatin, oh, that worked out really nice. You're on that side of the room. So you'll do the EDA part of it over here. So they'll be your breakout facilitators, if you will. And we're going to ask people to self-select which one they want to go with. However, we definitely want to make sure we have sort of a balance, that there's like 20 people here, and poor Dennis has 2. So we just want to make sure that we have an even distribution of folks. And Stan is going to be our floater to make sure everyone's, staying on task and making his contributions that way. Okay, so there's really 4 activities. One is a brainstorming activity where rapid fire, don't overthink it. You guys live in this industry. We're looking at what are the issues inhibiting growth and progress in EDA or EDA and IP, and just write them on the board. That's what we're going to do there. Then when we are done with that, we're going to move quickly to activity 2, where we'll look at all those problems and we're going to identify the top 3 issues or prioritize them. Okay, I'm being reminded we only 10 minutes. So again, rapidly doing this. Then we'll move to activity 3, and this is the activity that has a little bit more time attached to it, I think about 30 minutes. 20 minutes, okay. Where we're going to actually go in and sort of hack that and come up with a solution. Now, you have a choice here because you're going to have 3 identified problems or challenges. So you can collectively do that as a breakout session together on looking at all 3 of them, or you can break your group into 3 smaller groups and assign a problem to each of them and then come together and report it out that way. Considering the time constraints, it might be better just to break people out, because I don't know if you're going to get through all 3 in 20 minutes. So again, it's recommending the solutions and actions for those top 3 that you guys have prioritized. And then activity 4 is we'll have some report out from the leads on this, on what we found. It's all going to be captured very nicely in a graphic depiction, and we have some really good assets out of that. And I want everyone to hopefully have fun. And just, again, don't overthink things. Just kind of get the thoughts out and just dive in and let the energy flow. And that's pretty much it. And then I guess at the end of the day, we have a wrap-up on all of this. Because when we go back to your normal session, we'll be doing some magical things with all the results here so that we can report out at the end of the day and then have more of it displayed at the reception following. Dennis's team is going first. There's a lot of layers. Yeah.
Yeah, and that's in the way of our number 1.
Yeah, Yatin, we don't need that. They're going to go first, and then we can put it up.
Yeah.
So for Team Dennis, can we have our problem panel come to the floor here? Team Dennis, we need your presenters.
That means you two.
Yep. You'll go second, I'll go first, Trevor will go last, and I'll hand up the microphone to you. You ready? Oh, you have the handheld as well. Should we change? Yeah, why don't we change? No, you have to stay up.
3 minutes.
3 minutes. How many per? 1 minute each?
No, 3 minutes.
3 minutes each, okay.
3 minutes each.
The first one that we had is IP sold by EDA vendors represents a conflict of interest. It's natural that their verticals appear. And so EDA tools also being sold along with IP are okay. But that means that interoperability across different tools becomes a challenge because of the captive nature of either the tool or the data that exist. So we're brainstorming solutions. We say one way to resolve this is to resolve the interoperability through license exchanges that improve off of what we have today. So while Stan and I might debate that we are okay as is at the moment, the users say we have a long way to go and that we should, and I said, well, what's a positive word on that? And it came up and we said improve the solution, but the users all said the solution's poor. So we need to improve on that. But what we need to do is have an economic incentive for that to occur, because if there's an economic incentive, the likelihood of interoperability of the tools, the IP that is created from a tool supplier would be there. So let's take a look at the agreements we have in place and possibly improve the commercial contracts we have. And if that's not possible, could we even look and see with the protocol vendors, the people that are specifying the protocols that we build IP around might be able to help out, such as a PCI or a USB could actually come up with perhaps some interoperability test or even the creation of some of that as well. That would allow us to bring our things together maybe in a plug fest notion like many do with a hard implementation like PCI when they all come together to make sure their things all run. So I don't think we have the ideal solution there, but certainly have identified that it's happening and an economic benefit to extend out from one tool supplier with their IP needs to be in place if anything's going to happen.
Okay, good job. Next one.
Thank you very much. So what we have seen is that there is excellent semiconductor. Higher? Oh. So there's excellent semiconductor IP written in System Verilog, and there's also excellent IP written in VHDL, and they all work very nicely as long as they stay in System Verilog or they stay in VHDL. But if you try to put a system on chip together that has a piece of IP in VHDL and one in System Verilog, then quite often they don't play very nicely. They may play well in the solution of one EDA vendor, but not necessarily the same way in the solution of another EDA vendor. And that is a problem for the large semiconductor companies, as we have seen over the past few years. Now, one solution that was brought up was to get rid of VHDL altogether, and then it's all taken care of. But I am sure that there are many IP vendors, providers that would not be that happy with that, and myself being a representative of Verific Design Automation, where we license both System Verilog and VHDL parsers, we think two standards are better than one, right? Another potential solution that was considered is building a translator or a converter for the language so that you can actually take your VHDL, translate it in System Verilog. Those attempts have been made in the past and have not always been very successful, and there are some technical reasons why it even may never work. But finally, a third possibility, and it really has to come out of the semiconductor companies. They have to take a leadership or to push the EDA companies to come to an interoperability solution here. As I said, the larger semiconductor EDA companies, they have a solution of their own, but they're all different. So this is a clear example of failing interoperability, and I think that the Intels and Qualcomms and AMDs of the world, they have to come to the EDA world and push them to solve that.
Great, thanks.
Okay, so the challenge that I'm talking about is gap in SystemC standards for observability and debug and configurability. So we know today in SystemC we have pretty strong standards for model interoperability, so we can develop models to the TLM2 standard and we can connect them and we can be assured that they're going to do the right thing. However, when we look at how our model interacts with a tool, right? We're sitting at a tool and we want to be able to debug a SystemC model. We want to be able to see what the registers look like, what the bit fields are, what the accessibility rules are for those bit fields, what the configuration parameters are for the model. Down here we talked about how some companies are using performance observation points to get key information out of the model. All that wants to go out to a tool and to be displayed. And today the interesting thing is that it's not that we're missing a solution here, it's that we have dozens of them. All of the EDA companies have solutions for this. Many of the users in the SystemC space have solutions for this. And so if you're sitting in a very narrow world and you're not exchanging models with anybody else, life's not too bad. But if you want to pick up a model and give it to somebody else using a different tool, or you want to bring IP from somebody that's supplying models and put it into your tool, then you have a lot of problems. So this is something that Accelera is chewing on today. So that's the primary thing that we need to go after, is there's a working group in place to go off and define these standards. Probably the secondary issue here or challenge that we have is that getting enough people and the right people in and participating in these working groups. So if this strikes a chord with you, or you know somebody who it might strike a chord with, please contact Accelera, contact me. I chair the working group right now. We're actually just getting it fired up again. It kind of had been in a lull for a while, and very excited about getting this going again. So let me know if you can contribute in any way or have inputs for us.
Great.
Okay.
Great job. Anyone have any questions for the Team Dennis? Questions?
Sniper marks?
My question is, did you figure out the detailed plan of how to get rid of VHDL?
Yes, Trevor told us it was SystemC.
Next group. Thank you. Great job, guys. Okay, Yatin, team.
So you might need an extra mic.
Yeah, we have all our presenters up. Okay.
So one of the problems we thought that was plaguing EDA was the issue of the chips being very costly to build. So as you can read from all these papers and magazines, they talk about the chip cost running from tens of millions of dollars for older nodes to hundreds of millions of dollars for the newer nodes. And so one of the solutions that our group came up with was don't build chips. And so the idea being, as you probably heard Voj talk about earlier today, is you need to have all these modes in your chip and then really use software to figure out how to utilize their chips so that you can get, go from those 200 watt system to 75 watt system to 2 watt systems. And it's done with the same chips. So you pretty much customize around software rather than trying to customize around hardware. The second point raised was reuse IP and raise the level of abstraction. So by reusing a lot of IP, hopefully you can drive down the cost of your system. Unfortunately, the cost of IP itself is also quite large. So hopefully if there are multiple suppliers supplying different IPs, that cost can be brought down. The third solution that we talked about was 3D semiconductor printing. So instead of trying to build customized chips, perhaps the printing of those chips could perhaps be cheaper. So you can avoid the cost of masks, and hopefully the savings therein could possibly translate to building chips. And in that sense, you could actually build more chips because although the cost of building a chip could be slightly higher, you don't have to build a whole bunch to be economically feasible. Okay. multi-shuttle projects. So multi-shuttle projects have been very popular in universities and consortia to basically say, hey, can we put 25 projects on this one wafer and maybe do 20 wafer lot and pretty much give everybody a sizable size of chips to work with. Unfortunately, at the advanced nodes, we don't have these concepts, especially as we go to double patterning and triple patterning and so on and so forth. This is going to be pretty infeasible because on the same wafer, trying to get all the design rules solved and all the line fragments situated correctly, that's going to be very expensive. So if one could design a solution that, whereby multi-shuttle projects could be utilized, that would be one way to solve this problem. And I think the last one was basically university chips, which basically said the same thing, basically having a consortia that helps you do multiple projects on a single wafer, possibly reducing the cost of building chips.
Great, thank you. Okay, our next victim.
Okay, so the next issue that scored high on our list was return on investment. I think Dennis touched upon that a little bit earlier, the economic incentive. So I'll just go down the list here. Even though Shishpal said the solution to the first problem was not to build any chips, but one of the solutions to the ROI was actually build more chips. So we have to rectify that somehow, the two solutions here. Also, as part of that solution, there was discussion on having more customers, more users, so there will be more income for the providers of the solution. Common EDA marketplace. Let's see if I can. Okay, there you go. Yeah, Craigslist. There you go. Yeah. And the other solution was, let me see if I can, non-disclosure agreements. Enter, yeah, oh, okay, I guess that's, yeah, non-disclosure agreements. I guess that is the other solution to the ROI problem. The next solution is number of user. Can you read that? I can't read that. Or maybe you can read that.
Consortium of users.
Oh, consortium of users, right, yeah. So essentially, the capital will be provided by a consortium of users who are interested in that solution. So part of the investment problem will be actually rectified by the users, which is an interesting solution, I believe. So yeah, the pool of investment comes from the users. I think that's about it.
Okay, great, thank you.
Thank you. So the last issue was actually a very contentious one. It's about having a common database to represent your entire chip in all phases of your design so that anybody could poke into the chip at any point of time and get whatever information they're looking for. So, I mean, there's already probably some initiative from the Open Access Forum, and but I will go into the different solutions that we thought of. The first solution is to actually get user buy-in. Does everybody believe that there's a need to have some form of common database storage, and get users to, first of all, realize the need for such a database? The second idea is to think big data. Your whole chip is composed of different types of information, and the information gets refined over time, but you're still accessing the same sort of metrics. And it would be interesting to track these metrics over time. So instead of having tool proprietary formats for storing data and having to use a certain tool to extract information for a particular attribute, if you could think of it as like a big data and run some sort of a Google search on your database to get all the information you need, that would be great. But that's kind of thinking big data. I guess to talk about such a database, we first of all need some sort of standardization so that everybody can agree upon representing and capturing all the information in that sort of a database. And to that effect, what we need to do is check and see what sort of a prior art exists in this already, what sort of activities are already going in this regard about big data and finding database capture, database representation, and see if, and then you could also set up a feasibility study group. We have different organizations looking into this. So, if users and EDA companies get together and set up a feasibility study group, then we'll probably have more traction on this. But that was pretty much what this third issue was, which is having a common database to capture your entire chip information so that it could be accessed in a consistent format and it's tool agnostic.
Great.
Thank you.
Thank you. So do we have any questions for Team Jan?
Just so everyone knows, Susan was talking about one and not multiple. Oh, she's talking about not multiple large databases. She's talking about one big one.
Yes.
Okay, okay, just one.
We have distributed operating systems, we have large data servers, we have the capacity to aggregate information, and we also have capacity to distribute information. There are new algorithms to query, and then new database formats, Hadoop, blah, 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 whatever, to store and retrieve information. The problem is when you go with tool proprietary formats, the same information gets stored in different ways. For instance, Verilog has design information. Maybe Liberty has, some of the same information about PIN. IPExact could have some information which is about, ports and, bus formats. So you're kind of replicating information in many ways. The timing information or power information, again, there's a lot of replication over phases. So if you actually sum up the entire disk usage, you probably will end up using a lot more disk space when you have all different types of formats. I know this is a big idea. It's a giant leap to think you could go from Verilog to some sort of an abstract database. But the idea is, yeah, you want to derive Verilog, you want to derive your timing constraints or your UPF or your other metrics. But instead of having to do it in proprietary formats or in different, being able to represent all that in a generic database and taking advantage of all these amazing computer algorithms to optimize, search, and distribute data, you could probably come up with a more shorter version of the database if you just care about logical connectivity. Maybe you could do that. But the idea is, how do we even represent the data, and how do we make it searchable and accessible? I think that's the bigger problem.
Any questions? So we have a lot of great ideas here. We have the big, big ideas. Maybe some or they're all big ideas and great ideas, but out of all of what we've seen so far, what do we think is something more feasible, actionable in a shorter term? We started, I know in Yatin's group we started to have that discussion, like we started to put the solution, like, okay, well, what would be the next step? We said, okay, this is great, let's do something about it.
I'd say list the 6 items so that we know, again, to remind those of us with short-term memory.
Yep.